Right, so I think we can start. I think we've got a lot of people online already, and I think obviously we're going to get more to join. Firstly, thank you everyone for registering for the Jinko Solar webinar. We're very excited to have Kevin Robertson from Jinko South Africa presenting today. Kevin will be taking us through solar and quality introduction. So effectively, Kevin's going to share a lot of information with us today that is new to the market and some very interesting information on the progress and progression of solar panels. And I think we're all obviously very interested in hearing what he has to say, and I've read through the presentation already, and it's very interesting and very good. So again, appreciate everyone for registering and attending, and I hope everyone takes something away from the presentation today. Just to take you quickly through the procedures, so I'm sure everyone can hear us. We do mute everyone at the beginning of the webinar. If you have any questions, please feel free to put up your hand. If you look in the little in your taskbar at the top, there's an area to click to put up your hand effectively, and one of us will obviously attend to your question or anything that you have. If you also want to write a chat, you can write a chat to the host, or you can write a chat to anyone in particular, any of the panelists. So if you know one of the panelists and you want to ask a question, please feel free to write a personal message to the panelists, and we will obviously address it on the group. We will have a question and answer section at the end. I know Kevin will obviously be very receptive and very open to taking everyone's question. So it will be very nice if you can keep the questions to the end and everyone can ask what they need to ask. So before I take up any more time, let me hand over to Kevin to take over. Kevin, over to you.
Hi, good morning everybody. First of all, thanks very much to PROINSO for hosting this webinar, and thanks to everybody who's joining today. What I'll do today is just do a quick run through of Jinko in a nutshell. We'll look at some technology and quality, run through some key parameters on the data sheet. I'll look at some definitions around standard test conditions. We'll have a look at some cell and module construction, and then finally covering some issues around shading. So just to do a bit about Jinko. Jinko at the moment is the largest module manufacturer in the world by shipment volumes. We're a New York listed stock exchange company. We currently, I think it's number 330 in the China Fortune 500. Currently got 400 megawatts installed in South Africa, and then 5 factories in 4 countries. So there's 2 in China, 1 in Malaysia, 1 in Portugal, and then we've got a 144 megawatt facility in Cape Town. Currently we're producing for the US market.
Hi Kev, it's John, right?
Yes.
Are you busy sharing your screen?
Yes, I am. You're not seeing it?
No, I'm not seeing your screen.
Okay, let's just try something quickly. Is it now?
Yes, there we go. I see. Okay. Yeah, there we go. Fantastic.
All right, there's just having a look at those key figures that I just discussed. Okay, moving on. Jinko's got quite a wide range of products on the market. We've got our standard products, which is in South Africa, we're currently offering the 60 and 72 cell modules. Standard product range is 260 watt, and then 310, 315, and 320 watts. In 2015, we launched our Eagle module. The Eagle module is a PID resistant module. and it has a much lower temperature coefficient of power. So that particular module is 0.4% temperature coefficient of power. We also launched a smart module range. So the major smart module range that we have is a Tigo smart module, and the other one that we offer in the market is a Maxim module. The difference between the two modules is the smart modules is that the Maxim does a string level optimization, and the Tigo does a module level optimization, and it also has a monitoring portal as well, whereas the Maximum does not. It only does the optimization. Earlier this year, we launched a 1,500 volt module, mostly used for utility scale projects. We launched a black poly module, and at the end of this year, we will be launching a mono PERC module as well. So just the other module that we launched earlier this year is a dual glass module. The nice benefit of the dual glass module is that it has a 30-year power warranty. So that's quite a nice feature if you're looking at some of the other competitors. The other thing about dual glass module is obviously there is some transparency, so it's quite a nice module to use if there are some architectural features that you are looking at. It can be carport, shading, awnings, that kind of thing. Any questions so far? Okay, moving on to our R&D. Part of the requirement to be a Tier 1 manufacturer is that you have to have your own internal R&D department. We've got slightly over 200 R&D personnel, and the major research that they do is on materials as well as cell improvements. We've partnered with DuPont on advanced materials, and there's two parts to that. The first is on the cells, and the second is on the materials we actually use to manufacture the modules. So that is the backsheet and the EVA. We own our own patents on a number of processes, from ingots, wafers, cells, and module processing. And the R&D department does continual improvement. Some of the quality control systems that we have, electronic management system. So what that is it's an inline process where we do quality control from cells right through to the end module manufacturing. It ensures full traceability across the production line. So at the end of the manufacturing, we have the barcode, and we can track everything from which ingots we used, cells, people on the production line, and all the electrical data from the measurements. Jinko employs an electroluminescence test before and after lamination, and that test in particular is to measure if there are any defects in the cells. So that can be anything from cracks to micro cracks, anything that wouldn't be picked up with the visual inspection. And we also test the electrical characteristics of those cells. Some of the other tests that we do, this is not inline, but offline, so we take samples. We do power testing, cut testing on the back sheets, pull testing. What that is we pull the soldering ribbons off the cells to make sure that the soldering quality is correct. And then we do a number of environmental testing, hotspot testing, impact testing. Wet leakage is quite an interesting one. What we do is we submerge the modules in a bath of water. We inject voltage into the leads of the module, and we measure insulation resistance between the frame and the terminals. So we don't want any leakage current reaching the frame while it's in operation. Some of the other tests that we do, salt spray, ammonia testing, and junction box robust testing. Something that was quite important for us is Jinko Solar became the first Chinese module manufacturer to receive TÜV Q+ qualification. And what that means is that the standard for modules in the industry is the IEC 61215. With the Q+ qualification, we actually exceed those standards. It is now recommended by the California Energy Commission and looks like it may become a requirement in the future in the US. So part of the testing is we do actual performance testing in harsh environments. So modules will be installed in real life conditions in regions where temperature will fluctuate a lot, and we typically be in desert conditions. We do dynamic load testing on the modules that's not included in the IEC standards, and we do pressure and vibration testing as well. And what this does is it better reflects the mechanical strength of the module in real life conditions, which will ensure that we don't have any micro cracks on the cells under the environmental conditions. On those, we also do humidity and freeze testing on an ongoing basis. We do a much higher insulation test, and we do hotspot tests. So we're quite proud that Jinko is the first Chinese manufacturer to pass that qualification.
Kevin, I've got a quick question for you.
The other value, yes.
I just wanted to quickly find out by you. So Jinko, with the TÜV status, it is also UL. Is that correct?
At the moment, it's based on the IEC testing, but yes, it is. It also exceeds the standard UL criteria.
Thank you.
Okay. Any other questions? Okay, moving on. With Jinko, we've got much thicker wafers. What this means is that in the production and lifetime of the modules, you get fewer micro cracks. We've got 40 quality control checks across the production process. I'll cover it a little bit later, but we've got a much higher performance at normal operating cell temperature. We've got the lowest temperature coefficient amongst the crystalline silicon manufacturers, which is 0.4% per degree Celsius. And we've got a much better low irradiation performance. What I'd like to move on to now is a few of the key criteria on the data sheet that I feel are quite important and that sometimes people don't consider. So if we look at the electrical characteristics of the module, you've got your standard power under standard test conditions. So looking at this one, we've got our JKM 270 PP, which is our Eagle module, 270 watt peak. Our voltage at maximum power, current, and all those criteria. Why the voltage is an important one that is often not considered is that the modules have a temperature coefficient of voltage. So the voltage will decrease by 0.3% per degree Celsius above 25 degrees. But what it also means is that it increases by the same amount for every degree Celsius below 25 degrees. So quite often what people do miss out on is that in low temperature conditions, particularly in the Karoo, they will oversize these strings, and your voltage then becomes a problem because in those low temperature conditions, you'll have an overvoltage on your MPPT controller and your inverter won't turn on until that overvoltage condition has been resolved. So you can get a much later turn on of your inverter and potentially an earlier shut-off. The other consideration is your temperature coefficient of power. So once again, for every degree over 25 degrees, your power will decrease by 0.4%. So once again, that's quite an important consideration when you are looking at your energy yield of the modules. If we then look at our electrical characteristics, this is just a graphical representation of that of your degradation of the power according to temperature, and here is your open circuit voltage. So once again, in low temperature conditions, very important to consider your string sizing and your voltage window of your MPPT controller. Your solar cell is a current source. So what that means is that your bias on your solar cells remains fairly constant over your irradiation conditions. But the current in your module is reliant on the irradiation. So here, for example, we see 1,000 watts per meter squared. We're sitting at about 8.8 amps, which is fairly constant over your voltage range. As your radiation drops to 800, 600, and 400 watts per square meter, you can see that your current drops significantly as your radiation drops off. But once again, your voltage remains fairly constant. So looking at your power curves, which are a product of your current and voltage, you can see how your power drops off quite significantly according to your irradiation conditions. So there we're looking at your power window. So it's quite important to size your system within those voltage range of your MPPT controller.
Kevin,
this is just, yes.
Real quick. Particularly in South Africa, when calculating the volts in it, is there a very big difference in the temperatures here on the coastal line compared to the Karoo? And compared, for example, Durban to Cape Town in the temperatures?
No. At your coastal regions, the sea tends to moderate the temperature. So, for example, in Cape Town, I'd say typically speaking, you probably wouldn't go below 10 degrees. Maybe sometimes when it's really, really cold overnight, it might go down close to freezing. But, you know, once the sun comes up, your temperature increases quite rapidly. You know, for example, say a place like Close River or Beaufort West, you'll find early in your morning you've potentially got temperatures below freezing. You know, if you then look at your voltage, if you've got a string of 18 or 19 modules, potentially per string, you're looking at a 50 volt difference on that string. So if you've got a lot of strings together, it can affect your voltage if you oversize that. Is that all right?
Yeah. Thank you so much. I've just got another one, especially talking about the stuff here on the coastal line. Your modules, now for example the Jinko modules, does sea salt or anything like that do anything to the module? Does it affect it in any way?
Yes, sea salt is a consideration. Normally, if you move a little bit away from the coastline, it's not so much of an issue. Typically speaking, what you'll see in all of the module manufacturers is a decreased warranty if the modules are in a marine environment. But typically speaking, that would more be if they're on boats or platforms on the sea, lighthouses or oil rigs, that type of thing. With Jinko, though, we do have a, it would need to be specified, but we do have a module that is resistant to salt and sea mist. So if you are in a particular marine environment where that is a requirement, you just let us know, and we build a module with a slightly different bill of materials, and that particular module is resistant to the sea environment.
Awesome. Thank you so much.
No problem. Something else that you see on the modules quite often is your module efficiency. This is not normally I'd say an important criteria, in that if you're comparing modules of the same power class, you might see a difference in the module efficiency. So if we look at the formula, it is the product of your aperture being the area of your module, multiplied by your radiance at standard testing conditions, 1,000 watts per meter squared, and you divide your power by that product. So quite often what you see is you can manipulate your efficiency by decreasing your module aperture. So what that means is that you can reduce the area of your glass and receive a higher efficiency. Where this can potentially cause problems is that if your glass is too small and the distance between your cells and your frame is too narrow, you can potentially get problems with isolation between your cells and your frames. There is also, when your sun is at low angles, there's potential shading on the cells between the frame and between your frame and your cells. And the other potential risk is PID. So that's just something for consideration when you're looking at the module efficiency. This is another consideration, but you won't see it on your data sheets. Normally what will happen is if you get shipped a pallet or a whatever order you receive, you'll typically receive a fill factor on your flash sheet. Fill factor is just a indication of how well your module is performing. So it is the product of your short circuit current and open circuit voltage, your power that's divided by your product of your circuit, short circuit current and voltage. And what this gives us is it gives us an indication of how well your cells are performing. And typically speaking, for a solar module, you're looking at a full factor of something that is greater than 75%. That's just a consideration as well, something when you're looking at the flash data. What I want to look at now is your standard test conditions. Standard test conditions were set up so it's a benchmark for in the production testing to characterize your modules according to a power class. Your standard test conditions are 1,000 watts per meter squared, 25 degrees, and your spectral distribution at something called AM 1.5. So what does that mean? Your AM is your air mass coefficient, which defines the distance that the light travels through your atmosphere. So if we're looking at the top of the atmosphere, you've got a condition AM 0. There's 0 air mass. if your light is perpendicular to the Earth, at the sun's zenith, that is called air mass 1. And if we move 48.2 degrees away from the zenith angle, the distance the light travels through the atmosphere is 1.5 times. So that is AM 1.5, your standard test condition. Why do we consider that? If you look at your solar radiation spectrum, looking at the yellow portion, that would be your air mass 0, so the light spectrum at the top of the atmosphere. Because of aerosols in the atmosphere, you've got water and the various chemicals in the atmosphere, you have a filtering effect. So the red would be the typical light spectrum that you would see at sea level. If you then take it a little bit further, your solar cell will only convert a portion of that light. So this green area here is the light spectrum that your solar cell will convert into energy. So when we do our standard testing, we have to take this light spectrum into consideration, and it is a standard that has been set up by IEC as to how we test the module according to those that spectral distribution. So we've spoken a little bit about our standard test conditions. It is quite a nice benchmark for production testing, but for modules, something that is actually more important when you do your comparison is something called NOCT. So it's the module performance under normal operating cell conditions. Typically speaking, the cell temperature at NOCT is 45 degrees. Your radiation will be 800 watts per meter squared. Ambient temperature of 20 degrees. Your air mass 1.5, and you normally factor in a wind speed of 1 meter per second. So that is just considering a slight cooling condition. Having a look at our Eagle module, I've taken the 270 watt peak module as a benchmark. Under your normal operating cell temperature, your module then your peak power then decreases to 202 watts. So why is that an important consideration? If we look at these two modules, these are both 270 watt peak. So this particular module is 270 watt peak. Your performance at normal operating cell temperature is only 196 watts. If you look at our module, we've got a 270 watt peak, normal operating cell conditions, your power is 202 watt peak. So you're getting an additional 6 watts peak at your, what we'd consider a normal operating conditions. What that translates to is when you're doing your energy forecasts, you'll see that your production over a period of time will actually be a lot greater with a module that is performing, it's got a much better performance at your NOCT. What I'd just like to cover now is cell technology. Jinko's production at the moment, about 6% of our production is mono cells. Typically speaking, what happens is you have your silicon material which is melted in a crucible. You then have a inside with that rod is turned slowly and slowly withdrawn from the bath, and what happens is you get a single uniform crystal structure forming like this. The crystal is then cut into wafers, and the wafers then go cell manufacturing process. Historically, you saw a circular cell, but the problem with that is it was not very efficient in terms of space. So what typically happens now is the wafer is sawed into more of a square shape, and you get the rounded corners. So the easy way to identify the mono cells is you get a nice uniform color across the cells, and they have a rounded corner. The problem with the mono cell production is that it's a lot more expensive because your conversion of your silicon material into a crystal is a lot less efficient. There's a lot of wastage from the material that is cut. The advantage, however, is that you do get a high efficiency module. Where that is useful is where you've got areas where you need a much higher peak power. So typically speaking, we see a lot of mono cells in areas like Japan and the US where you have space premium on your roofs and you've got high feed-in tariffs. If we then look at our polycrystalline cells, what happens in this case is the silicon material is goes into a furnace, it gets melted and then poured into a crucible. So it's very similar to the manufacturing process of gold bars. The silicon material is then cut into the wafers and go through the cell manufacturing process. During the cooling process of the cells, you don't get a uniform crystalline structure like your mono cells. As the material cools, you get multiple crystals forming at the same time in different orientations. So that's typically speaking why in a polycrystalline cell you see the texturization. That's the different cell the different crystal structures inside the cell. Why is the polycrystalline an advantage? They're much less expensive to produce, and you get a lot less wastage from the manufacturing process. There's a slight disadvantage in that they are less efficient, but what we tend to find with the polycrystalline cells is that you actually get although you don't get the power, you get a better low light performance. So they're not necessarily worth paying the premium for a monocrystalline panel. The other advantage with crystalline technology and polycrystalline technology, there's a lot of research going into the cells. So we're seeing that the gap between the polycrystalline and monocrystalline is closing quite a bit. Now looking at the module construction. So typical crystalline module construction is a glass. It's a low ion tempered glass, and it can be with or without a anti-reflective coating. On the inside of the glass there is a texturization. Basically what that is a slight pyramid type of structure. And the glass is designed like that so that if there are any reflections of light off the cells, off your white backsheet, the prism structure inside the glass will then reflect the light back into the module. So it's just a way to maximize the efficiency of the glass. Then you have an encapsulant material. It's called ethyl vinyl acetate, or EVA. Very similar to material in a hot glue gun. Next layer is the solar cells. In the manufacturing process, the cells are sold together with ribbons in a machine called a tabastringer. The tabastringer makes up the strings. The strings then get soldered together to make the series connection. We then place another sheet of EVA on top of that, and then a back sheet. So it's a tethered polymer, although with some other manufacturers you do get other variations of that material. What then happens is this laminate goes through a machine called a laminating machine. During the process, your encapsulant material, the air in the laminating machine gets evacuated. It's typically speaking between 125 and 140 degrees, depending on the encapsulant material and the recipe you're using. And the module will sit inside that laminating machine for about 25 to 30 minutes. What happens in this process is the EVA starts to melt and you get cross-linking between the two layers. That encapsulates your cells and it bonds your different layers, the glass, the cells, and the backsheet together. After that, we trim any excess material off the laminate. We put the frame on, and finally the junction box gets added to the module. The final thing that I would like to cover today is a little bit about shading. Shading is quite often a consideration that doesn't get factored in when doing installations. So this is particularly a problem when we move further south. So your sun path during the summer and your winter months is quite different. So there is potential shading from obstructions that you might not consider if you're doing site assessments in the summer and winter time. So that's just an important consideration, your site assessment, to make sure that there is no shading. What happens in the module when we have shading? Because your solar cells are a current source and your solar cells are connected in series, what happens is if you have shading, the entire string then will produce zero power. So the way we get past that is we have, if you're looking at this, this is your equivalent circuit diagram of your solar panel. So here you have your solar cells in series. What we then do is we put what's called a bypass diode in parallel with those strings. What this allows is that if you then have shading on a solar cell, your bypass diode will go into what we call a forward bias condition, and effectively you'll take that string that is shaded out of the module so that it doesn't affect the entire module. What this then means is that you will lose, in that shading condition, you'll lose 1/3 of the power in your module. Why is that important? In your shading, when you're doing the layout of your array, very important to consider, because if you have shading across your strings, such as this condition over here, what will happen is the power in your module will reduce to 0. If your shading occurs across this string, you're only losing the power in that particular string. Your bypass diodes will go into forward conduction. That string will be shorted out of the module and you'll only lose the power in that particular string. So just looking at an example, if we look at the first picture, we have no shading on this array. And here you can see you have a nice power curve. When we go into a shading condition, you can see how the bypass diodes, when you go into forward conduction, how the power of the module drops quite significantly. So shading is a very, very important consideration when doing the layout of your arrays. There are ways of getting around this, and that's where our smart modules come in. I've mentioned before we have the TIGA and Maxim optimizers on our built-into our modules. What that then does is, instead of affecting your entire array, only the portion that is shaded will get affected. So in this example, you've got 8 modules in series. Here in the shaded example, you have shading on some modules, and your production drops down quite significantly. In the optimized solution with the TIGA and the Maxim modules, in the shading conditions, you find that only the affected modules will drop out. So each of these modules that are not shaded then perform at their optimum. So depending on the shading conditions, you can get 18 to 20% better production where you have shading in the array. So just looking at the voltage on the module, typically speaking, you will have an even voltage across your the strings. So if you have shading on a string, the particular portion of the module that is shaded will then drop out. So in this case, if you have one string dropping out, your voltage will then drop down to what's that, just under that's 39 volts, 39.2 volts. So this is a real life condition, just to show you how the power gets affected by this condition. This particular module over here had a problem with it. If you use an infrared camera, this is typically the kind of image that you will see when there is the bypass diodes are in operation. Because the bypass diodes are in operation, this particular string started to get slightly hotter. If you look at the actual measurements on the graph, you can see here the voltage has dropped down to what are we sitting there at? About 24. Let's look on the graph. Yeah, the 22.3 volts, as opposed to an expected 34 volts. In this particular case, it was actually a problem in the junction box. So the string was the bypass diode was in. It has been forward biased all the time. Once the junction box was repaired, you can see that the voltage is back up to your normal 34 volts. So in this condition, the module performance was 63, and once it was repaired, 96. In a shading condition, you'll get a very similar type of performance from your module. The final thing that I'd just like to show you is the performance of the module in different orientations. Quite often, when you're doing installations, the customer will say, well, you've done a 3 or a 5 kilowatt system, but I'm not achieving my peak power. So why is that? If you look at your module performance, typically your power or yield is not affected if you move about plus minus 10 degrees away from optimal conditions. But as your module moves out of the optimal conditions, your power does drop off. And that is also affected by how the panels are mounted if you've got any ventilation. So just a graphical representation. It's an easier explanation about how your power is affected according to orientation against the sun. And thank you. That concludes my presentation.
Thank you so much, Kevin. Thank you so much. So we're going to make it open now for anybody that want to have or have some questions. So please feel free if you've got any questions. We've still got a bit of time. So raise your hand on the right hand side. Just click and we'll unmute you, and you can speak or message either myself, Matthew, or Russell, and we will ask the question. Kev, I've got a question for you. Just with this last point, for example, if you get a hotspot on the modules, what is the main reason why you get a hotspot? Is it a cell deficiency? Is it maybe a crack over time? How do you get, for example, on where I'm sitting there now, on the left hand side, it looks like two spots there on the left hand side. But
you're looking at those?
Yeah.
You're looking at those two. Okay. What you're actually seeing there is just because of the resolution of the camera, that those spots there are actually the junction box behind the module. This particular camera is quite a high resolution camera, so I think that the difference in that particular case was only about 1 degree difference. But if you are looking at the module and there are hotspot issues, there are a number of things that you can see. Typically speaking, the difference in temperature, sorry, just the different colors there just represent the different temperatures. Typically speaking, you can have soiling on the module that only affects a cell, so that can be anything from bird droppings, a leaf, any soiling. It can also be a damaged or broken cell. So what could happen is during the installation process, you might have micro cracks in the cells. Over time, those micro cracks, so what it does is inside the cell, it actually creates a resistance. With the current passing through, because of the increased resistance, your cell temperature will increase, and over time that does get worse and worse. So micro cracks are another issue, and then sometimes we do get defect cells. So potentially a defect cell which wouldn't be picked up in production with your electroluminescence or power test. Over time, that defect will get worse, and a hotspot will develop. The final thing that can happen is if your module is not laminated properly, you could potentially have bubbles in your EVA, or what we call delaminations. So over time, those bubbles or delaminations start to grow, which then causes shading internally on the cell, and that will also develop a hotspot.
Okay, thank you. We've got...
sorry, there's actually... Sorry, just one other thing that it can potentially cause a hotspot is the soldering on the cells. So if your soldering of the ribbons on the cells is of a poor quality, once again, it creates a resistance in your electrical path, and that increased resistance will then, over time, also develop a hotspot.
Okay. Thank you. Thank you, Kevin. We've got a question here from Linda. I'm going to unmute you, Linda, so when you're ready.
John, Kevin, thanks, guys. I appreciate your presentation, it's quite impressive. I just need to perhaps ask a couple of questions, maybe starting with the embedded optimization, which I picked up earlier on at the beginning of the presentation, that your modules do have embedded optimization. Is that correct?
Yes, we do. We've got
the main two products that we have is the Tiger optimization, and the other one that we do is a string level optimization with Maxim.
Okay, my question obviously is around the branding, whether your modules need to actually comply with a specific brand of inverters, or any inverter is compatible with those modules with embedded optimization.
With the Tiger optimizer, we can use it with any inverter. The only thing that you need extra with the Tiger optimization is Tiger uses gateway, because they do module level monitoring as well. So in addition to the optimization on the back of the module, which is embedded, you then need to purchase a additional gateway, which is a communication protocol between the module optimizer and your monitoring portal. With the Maxim module optimizer, it's not a smart module. So in other words, it does optimization across every string. I just want to try and hear. Okay. So in this case, with the Tigo module, if we look, your optimization is done at module level. So your optimizer will sit across your positive and negative terminals. So if you get a shading condition across one string, your bypass diode still goes into forward bias conditions, and you'll lose a third of the power of that module.
Right.
But with the Tiger, we still have the communication protocol so that you can monitor the performance of that module. With Maxim, they go a level further. Now, what they do is their optimizer sits across each of the cell strings over here. So effectively, you have 3 optimizers built into the module. So the resolution of the optimization is much greater. So in shading conditions, you get a much better performance out of those optimizers. But they're not a smart module in that they don't communicate with. So there is no actual monitoring built into that particular optimizer. But once again, in that case, you have the ability to use it with any of the inverters on the market.
Okay. All right, fine. Thanks. Quite impressive. Right. So while you were talking about that, obviously there are diodes, bypass diodes in the mix, which you were talking about much later on. Now the diodes, sometimes, as we all know, sometimes do go faulty, either they short out, or they just sort of go open circuit completely. What would be perhaps the easiest way to identify that? I'm talking now in terms of the operation and maintenance environment.
Okay. The easiest way to see it is if I'm just going to use this graph as an example. So if you have a condition where your bypass diode is in forward conduction all the time, you'll see that your production curve will look something like this. So there is a knee in your production curve, and then you know that that diode is short-circuited. If you have open circuit condition, what happens is when you have shading, you will lose the entire production of that module. So if one cell is shaded, you'll get 0 production out of that particular model.
Okay, so then it will show back on your monitoring screen, basically.
That's correct, yeah.
Okay. Now, which brings me to the issue of identification. Your modules, will they be, what shall I say, uniquely identifiable, within an array? Obviously, I'm talking either whether with optimizers or without.
From the front of the module, there is no way to determine because the optimizer is actually built into the back of the module. I just want to look for something here quickly. Can you, is the screen still shared? Can you see that?
Yes, yes. Yes, I can see that.
So in this case, this is the TIGO module. So you can see the electronics is actually at the back of the module inside the junction box. But if you're looking here at the front of the module, there is no way to tell the difference.
Yeah. Oh, okay. No. I was actually talking. Yes, I'm with you, but I was actually talking with regard to your monitoring facility, where you monitor strings with a unique ID number of each and every string through your communication portal. I mean, not necessarily on a physical scale.
Exactly.
Yeah.
Yeah. Okay. So with the TIGO modules, with your optimization, there will be a unique identifier. When you do your installation, you have a tool where you can do your module layout. Each of those modules, you will record the serial numbers, and in your monitoring portal, you'll have your layout. So it is very easy to, if you're looking at the background picture here, you can see the layout of the modules. And you'll be able to do the module level monitoring with a unique identifier. It will be a serial number. Very easy to identify any problems in those. And you can look at daily production, hourly production, monthly, yearly in that portal.
Okay. All right. So that talks about those ones with the embedded optimizers. The ones without?
Yes, that's correct.
Yeah.
The ones without? No. That would be subject to whatever monitoring software you have with your inverter. So in that case, depending on how your monitoring is done, you would only have string level monitoring.
Okay. All right. Okay. No, that's fine.
Or monitoring, whatever, according to you.
Yeah. All right. Thanks a lot, Kevin. Right.
Thank you. We've got Kevin. We've got one more question. Vessel, if you are still there, you are unmuted.
Kevin, thank you for the meeting. Can you hear me?
Yeah, we can hear you. Go.
Yes, okay.
Okay. I just want to ask. You said there's deviation on hotspots. What is the degrees that you're looking at? Because I have worked with thermal imaging cameras. Your averages are normally, but is there a 5% increase or 15% increase, or where will you start picking it up?
That depends on the resolution of your camera. Yeah, I think in this case that was it was something like 1 or 2 degrees. And the way it was in this particular instance, what happened was we flew a drone over the solar farm, and the drone actually picked up the problem with the modules, and then we went in and investigated. So it really depends on the type of fault and how bad it is. The differences can be quite significant, and in severe conditions, I've even seen cells that have burnt and burnt holes in the white backsheet. So it can be from very small 1 or 2 degrees up to 15, 20, 30 degrees.
Thank you.
Thank you, gents. If there's anything else, any more questions? No, I think that's it. Thank you very much, Kevin, for your time, and for Jinko for this training session today. If you've got any further questions, you're welcome to contact either Russell, Matthew, or myself, and we'll be able to send more stuff. The webinar was recorded, so if you feel that you want to go over it again, we will be editing and uploading it shortly to our channel. If you've got any inquiries about pricing, anything like that, you can contact one of our friendly staff members or visit our website at www.proinso.co.za, and we'll have pricing and everything for you there. But for now, thank you very much, everybody. Thank you for your time. Thank you for attending. Thank you, Kevin. And we'll hope to see you on our next webinar. That is on the 8th of September. Yeah.
Before you go, if there is a requirement from your customer base, we can always, in a future date, host a separate webinar specifically looking at the smart modules with optimization.
Yeah, sure. That's good. That's good. But for now, thank you, everybody. We'll see you soon. We'll see you at our next one. Just for now.
Thanks, everybody. Bye-bye.